above. So without further ado, it's our pleasure to introduce our first speaker for the afternoon, who's Professor Andy Neitzke from mathematics at Yale. And he's going to tell us about geometry of n equals 2 supersymmetry. Take it away, Andy.
So thanks a lot for the invitation to give these talks. It's really, it's a great pleasure. So as the previous speaker said, I'll just kind of re-encourage everyone to speak up, you know, the moment something comes to your mind that you want to hear about. I mean, probably many of you, or almost all of you, know what it's like to be giving a Zoom talk. It's even more difficult than usual to tell where your audience is at. So help me out if you can. So what am I going to talk about? So this is kind of, these talks, I'm almost giving like a service course. They're not going to contain anything that's very new, I don't think, but it's a review of some kind of classic stuff about n equals 2 supersymmetric field theory. And the broad plan is kind of like this. So I'm going to say a little about what an n equals 2 supersymmetric field theory actually is. But the main thing I'm going to tell you is that there are a bunch of examples, particularly field theories that are built from a compact Lie group and a representation. Those are called Lagrangian field theories, gauge theories. Theories that are built from a Lie algebra and a Riemann surface. Those are called theories of class S. So I guess here I should draw a little picture of what it is. This is a little Riemann surface. And theories that are built from a number and a Calabi-Yau manifold. And these are called Calabi-Yau threefold. I guess more precisely, a non-compact complete Calabi-Yau threefold. And these are the ones that are called geometric engineering. So I'm going to tell you a story which in its most general form, it begins with an n equals 2 theory, which is to say concretely, it begins with one of these sets of data. So you could imagine we begin with a compact group and a representation. Or you can imagine we begin with a Riemann surface and a Lie algebra, or you can imagine we begin with a Calabi-Yau threefold. And given n equals 2 theory, there's lots of things you can do. I'm going to emphasize one of the particular things you can do, which is you can make out of it a complex integrable system. So as we go, we'll say what a complex integrable system is. But for now, maybe it's good enough to have in mind a picture very much like the pictures in Monica's talk this morning, namely like the one-dimensional case of a complex integrable system is literally a torus fibration over some complex one-dimensional base. So it's a space which is fibered over, it's a two-dimensional complex space, which is fibered over a one-dimensional space. It's complex symplectic, and the generic fiber is a compact complex torus. Then you have some singular fibers, which are more interesting. And the ones we have won't be as interesting as the ones in Monica's talk. I'm going to stick to relatively simple singular fibers. So all right, so that'll be the first thing is we start with an n equals 2 supersymmetric field theory. We produce, following Seiberg and Witten, we produce a complex integrable system. And then from there, then we're in a position to do some fun mathematical things. We can produce things like we can produce hyperkähler metric on the total space of the complex integrable system. We can study quantizations of the complex integrable system. We can study closely allied things like the BPS states, so some enumerative invariants associated to this system. And so I guess I should draw also an arrow here. Okay, so anyway, so this is the kind of broad outline of what we're going to do. I'm going to tell you, starting from an n equals 2 theory, there's a complex integrable system, and the n equals 2 theory gives you a kind of interesting way of thinking about the complex integrable system, which in particular allows you to understand things like its hyperkähler metric, its quantization, and so on. So that's the broad plan. And I should say that in n equals 2 theory, of course, in the state of things in the year 2021, an n equals 2 supersymmetric field theory is not a rigorously defined mathematical object. And so this upper left box is a little bit, it's still a little bit shrouded in mystery. On the other hand, the other two parts are perfectly rigorous things. And so by the end of the lectures, we'll be able to formulate, actual conjectures and in some case theorems about these objects that come from the n equals 2 theory point of view. Today, there probably won't be so much of that. Okay, so that's what we're going to do. But I feel like I have to start out kind of, a little more concrete maybe. So I want to start by giving you some indication of why, as mathematicians, because I guess at least some of you are mathematicians, why as mathematicians, you might be led to care about n equals 2 supersymmetric field theories. So let me start with kind of a story. It's the story of Donaldson invariance. If someone here is like a expert in Donaldson theory, I hope you correct the naive things that I'll say. But let me tell you this story as I understand it. The story's like this. Suppose you're given a 4 manifold, say a smooth 4 manifold. And you want to study its topology. Well, there's a cool trick for how to get like topological invariance of this of your 4 manifold. And the idea is to do something that at first sounds nuts. You equip it with more structure. You add a Riemannian metric. So the idea to construct topological invariance of X, you first equip X with a Riemannian metric. And then having done that, then you can formulate, well, you could formulate all kinds of things, but in particular, you could formulate differential equations on the manifold that use the metric. So you could study differential equations on X that use G. So differential equations that kind of canonically live on this Riemannian manifold X comma G. So what's the most basic example of that? The baby example of that you might think of first, but it's a very beautiful example, is to consider the Laplace operator acting on differential forms on X. So what is the Laplace operator? So, to write it concretely, the Laplace operator on differential forms, it's what is it? It's d star alpha plus d star d alpha. So you use the exterior derivative operator, which doesn't involve a metric, and its adjoint, it's kind of L2 adjoint, which does involve a metric. You put them together into this Laplace operator, and then define. So then we consider the equation. We consider all the forms that are annihilated by alpha, the harmonic forms. So I'll write HK. It's a vector space, and it's just the kernel. It's just all the forms, all the K forms on X, such that the Laplacian of the form is 0. So okay, that's some linear partial differential equation on defined using the data of x and g, some linear PDE to be obeyed by alpha. Because it's a linear PDE, the space of solutions is a linear space, and that space in detail depends on the Riemannian metric that you took. But there's a beautiful theorem, the Riemannian-Hodge theorem, which says if I define BK to be, well, one consequence of the Hodge theorem is that if I define BK to be the dimension over R of this space HK of XG, it is just the kth Betti number of X. So whatever is your favorite way of defining the kth Betti number. In particular, it's independent of G. So it really only depends on X. So it's, in other words, it's a topological invariant of X. Okay. So that's already, that's already pretty good, right? So in that way you can learn about the Betti numbers, the dimension of the cohomology of X. Oh, I should have said, sorry, compact. So absolutely, for this to work, X better be compact. But suppose X is compact, then then these are in particular are finite numbers, and they are the Betti numbers of X. So okay, so that's a way of getting topological information about X by studying PDEs that live on X. But the needs of topology didn't stop with the Betti numbers. And in the early 80s, Donaldson had a rather beautiful idea for how to go beyond this, using not linear equations but nonlinear equations on X. So this was the baby example. Now here comes the non-baby example. The idea due to Donaldson. And that's to do the following. So instead of considering this vector space, which I called HK of XG, the space of harmonic forms, we'll define a new space, which I'll call M of XG. And yeah, so we could do this for any Lie group, but following Donaldson, let's take the Lie group SU2, compact Lie group SU2. And now let's consider the moduli of G bundles with connection. G bundles over X with connection. Connection nabla, such that the self-dual part of the curvature is 0. And I'll just remind you what the self-dual part means. So recall F plus means 1/2 of, so this is something you can only do on a 4 manifold, is I can take F, which is a 2 form, the curvature is a 2 form. I take star F, which just on a 4 manifold is also a 2 form. And so then I take their sum, that's again a 2 form. And so that's called the self-dual part of the curvature. So this doesn't say the connection is flat, it's weaker than that, but it says that it's kind of half flat, half of the curvature is. So those are sometimes called, connections with that property are sometimes called Yang-Mills instantons. And so this is not a linear space. So this equation here, this is a nonlinear PDE. And if you write it out in detail, you see why it's nonlinear, by the way. It's nonlinear essentially because the nonlinearity comes from the fact that SU2 is not abelian. So so because we use a non-abelian group, the equation is nonlinear. It's not so this is some complicated equation. So the space of solutions is not a linear space. It has components of various dimensions. Yeah, in fact, I've already specialized to SU2, so I can say it a little more precisely. It's the union of pieces labeled by a non-negative integer k, the so-called instanton number, and the dimension of the kth component is 8k minus something that's independent of k. So it's basically 8k, but then there's a correction, and the correction has to do with the Betti numbers. B1 and B2 plus. B2 plus means the space of self-dual harmonic two forms. So okay, it's more or less a manifold of this dimension. It has a natural orientation. And so from this, okay, so now you started with your four manifold. You built this kind of complicated thing, which is the moduli space of instantons. Maybe you want to get some actual numbers. Well, it turns out that this moduli space also has natural closed differential forms. Call them tau alpha. Labeled by homology classes in our manifold X. And I think, if I remember right, the degree of tau alpha is 4 minus the degree of alpha. And so then what you can do is you can consider integrals, which I'll write like this. So this is just notation on the right. So O alpha 1, O alpha 2, up to O alpha L. So alpha 1 up to alpha L are these homology classes on our four manifold. That's going to be a number. And what number is it? It's the integral over the instanton moduli space of the product of these differential forms, tau alpha 1, wedge tau alpha 2, up to tau alpha L. So those are the numbers that that Donaldson defined. And now the crucial thing is that just like in the linear case, we have maybe unexpectedly, we get some topological invariance here. So these are numbers which are defined a priori using a metric on the surface, sorry, on the four manifold. But then in fact, the statement is that these are topological invariants of X. There's a technical condition. They're topological invariants of X as long as B2 plus of X is bigger than 1. But they're still interesting if this condition is not satisfied. They're just not quite topological anymore. They're slightly more interesting. So, okay. Any questions or comments at this stage? Okay, so these are they're powerful invariants in four manifold topology. On the other hand, they're somehow very difficult to work with. in particular, the sort of famous reason why these invariants were difficult to use is that the moduli space of instance on. So you start with your favorite four manifold, nice compact four manifold. You give it your favorite Riemannian metric, and then you study this moduli space. And the trouble is that this moduli space is typically not compact. And so you can see right away that that would cause you some trouble, right? Even I wrote down an integral, but that integral a priori is not even defined because M is a non-compact space. So Donaldson and people who came after him had to work quite hard to get sort of interesting results out of these invariants. Now, so this is where the story of topological quantum field theory kind of gets started.
Andy, maybe I have a quick question.
Yeah.
I mean, this is only going to make the problems worse in a sense, but just going back to your original assumption about G, I mean, one could consider, reductive but non-compact groups.
Oh God.
Okay, your reaction says everything there. I was going to ask what the utility, if there's any utility really in going in that direction.
Well, the short answer is I don't know. I mean, you could ask a similar question just about like going to SU3 or something. You could ask, do you get more powerful invariants by using other Lie groups, right?
Mm-hmm.
And so I'm actually not, I'm not like authoritative on this, but my impression has been that the answer is basically no. But maybe we'll return to that a little later, actually.
Okay.
Okay. So far I told you about some topological invariants of a four manifold. They're defined by just solving some PDE problem. But now the key observation, or a key observation in this story came from Witten in, I think, 1988. And I guess you could maybe summarize it like this: the story of Donaldson invariants is part of the bigger story of four-dimensional quantum field theory. But more exactly, it's not about the most general kind of four-dimensional quantum field theory. It's about some very specific four-dimensional quantum field theory. Well, actually, let's do it in two steps. So four-dimensional n equals 2 supersymmetric quantum field theory. But moreover, it's about a very particular one, namely four-dimensional n equals 2 supersymmetric Yang-Mills. So in short, what he said is the story of Donaldson invariants is part of the story of a particular n equals 2 supersymmetric quantum field theory, namely four-dimensional n equals 2 super Yang-Mills theory with gauge group SU2 and matter representation trivial. Okay, so that's what I want to tell you first. And at first, it won't be clear why this helps. And in fact, at first, it doesn't help. Just knowing that it's part of a supersymmetric quantum field theory, that doesn't right away give you any new way of computing. Well, maybe I'll already say here what the kind of punchline is going to be. So Witten in 1988 figured out that Donaldson invariants have to do with four-dimensional n equals 2 super Yang-Mills. That doesn't help you unless you're really good at understanding four-dimensional n equals 2 super Yang-Mills. And in some sense, in 1988, physicists weren't that good at understanding that theory. But Seiberg and Witten in 1994 gave a solution of, let's say, the low energy dynamics of this field theory, 4D n equals to super Yang-Mills with gauge group SU2. And their solution, okay, as I'll describe, their solution rather remarkably had to do with a complex integrable system over the plane, with two singular fibers like this. So rather unexpectedly, it turned out that in order to make computations such as the computation of Donaldson invariance, to make them in kind of a simple, effective way, the key technical tool that you need is a certain torus vibration, which a priori appears nowhere in the original setup. So that's kind of the surprise.
Excuse me, when you talk about tori, you don't mean one complex dimensional tori, you mean general tori.
Well, in the particular case of this particular field theory, like the particular field theory, which is n equals 2 super Yang-Mills with gauge group SU2, then I literally do mean one-dimensional tori.
Oh, okay.
But you're right. I mean, for a more general n equals 2 theory, they would be some high-dimensional compact tori,
Okay.
complex tori.
Yeah, thank you.
That's great. Other questions? Okay. So then,
Wait, sorry, could you say a little bit about what you mean by solution?
well,
Like,
okay.
Effective field theory, or like
Yes.
a solution to that field theory, or just like
No,
finding the field theory?
It's finding the effective field theory. That's really kind of 9/10 of the 9/10 of the work. Okay, there's well, yeah. I'll say more about that at the end when I get to it. But in short, yes. By solution, what I mean is writing down the effective field theory that describes this this quantum field theory at low energies.
Okay, thanks.
I might as well say it since you asked. So they wrote down the effective field theory at low energies. There's still some additional work involved in using that effective field theory for any particular four manifold, and that's roughly the job of the community that studies Seiberg-Witten invariance. So I don't want to say that once you write this thing down, it's completely trivial, but it's somehow much easier than dealing with the original Donaldson theory. Okay, so I feel like I should try to say something about what is a four-dimensional quantum field theory. So as I say, I regrettably can't completely define what a four-dimensional quantum field theory is, but very roughly, a 4D QFT, I'll call it T, is a machine, a very sophisticated machine, which assigns objects, invariants, to manifolds of various dimensions, less than or equal to 4, of dimensions less than or equal to 4. And these manifolds, they may be equipped with additional structure. They usually are. Okay, so I'll call the manifolds X. And X, the input to this machine is a manifold, but it may be equipped with something. So it might be equipped with a spin structure. It might be equipped with a Riemannian metric. It might, be equipped with like a framing, a foliation. People have considered by now many, many variants. One thing that'll actually come up for us is it might be equipped with an H connection for some group. for some group H, which is sometimes called the global symmetry group. So I'll call it that. Okay, so it's going to be a machine which what you put into the machine is manifolds equipped with all of this structure, and maybe also containing defects. So they can have all this structure, and then they can also have defects supported on submanifolds. So for example, and the main thing that we'll use today, so the object, by the way, that we assign to a manifold X, I'll call ZT of X. So for example, you might have X as a closed four manifold. So a compact four manifold without boundary. Then ZT of X is just a number, a complex number. So we're in pictures. Here's X. Then ZT of X is a number. Now, and as I said, it might also be decorated with some defects. So maybe here's X. And then here I have a bunch of marked points. And at each point, I have some local label. I'll call them O1, O2, and O3 at the points. Well, and the points are labeled X1, X2, and X3. So maybe I'll write it like this: O1 of X1, O2 of X2, O3 of X3. And in this case, what the machine assigns to X with these insertions, so it's again a number. But now there's also another notation for it, which is you write O1 of X1, O2 of X2, O3 of X3, like this. And maybe I'll write T here to emphasize that we're computing correlation function in the theory T. That's again a number. So up here, I could have also written this as the angle brackets with nothing inside because there were no insertions inside. So that's just numbers. Then we could have, as you go down in dimension, the objects actually get more complicated. So like I could take X to be a closed three manifold. Okay, so I guess here I should draw them like this or something. If X is a closed three manifold, or let's say if Y is a closed three manifold, then there's Y. Then ZT of Y. So now it's not a number, but it's kind of one categorical level higher. So it's a vector space. So to a three manifold, we attach a vector space, which you think of as being like the space of quantum states of the theory, formulated on a space which is kind of Y cross R, if you like, or some infinitesimal neighborhood of Y and Y cross R. And then if X is a manifold with boundary, say a four manifold with boundary, then you can have something like this, boundary. Then ZT of X. So before it was a number, if the four manifold was closed, it would be a number. When the four manifold has a boundary, then we get an element of the space of states on the boundary. Obeying some kind of gluing rules. So if you, well, all right, I think you probably, if you've studied topological field theory, you'll see rules very much like this in the context of topological field theory. There, it can be made into really a rigorous story, the story of extended topological field theory. Here, in the world of non-topological theories, I think this is not yet, this kind of functorial field theory is not yet a completely smoothly running machine, but nevertheless, it gives us some idea of what kind of thing we're aiming for. Okay, and as you go further down in dimension, you get more and more complicated kind of categorical objects. which we won't need today, so I won't even try to go into them. Okay, so anyway, so a four-dimensional quantum field theory is a pretty rich and complicated structure. And in this talk, and probably in all the talks, we'll use only a small part of it. Okay. All right, so all that is just some general nonsense about what a four-dimensional quantum field theory is supposed to be. And for our purposes, the main thing to remember is the stuff near the top, that if you have a four manifold, it's supposed to assign a number, and moreover, you're supposed to be able to make some insertions at points or along higher dimensional submanifolds, as we'll use later, and get in every case get a number out. Okay. So the particular kind of n equals 2 supersymmetric field theory that I want to use today, the one that Witten used for Donaldson theory, is called super Yang-Mills theory. So let's say what that is. Let's say heuristically what that is. So super Yang-Mills. So what's the data? A compact Lie group G. A finite dimensional complex representation. Finite dimensional complex representation of G. I'm sorry, would you excuse me for one moment? Oh, no one can see me. I can't see anyone. Someone's knocking on my door.
Oh, yeah, take your time.
Hey, John, it's nice to meet you. I'm just in the middle of giving a lecture.
So another time, I just wanted to say hello.
Yes, I would love to. If you're still here in like half an hour, I'll come by your office. Okay. Yeah. Hi, folks. Sorry about that. So we're given a compact Lie group and a finite dimensional complex representation of the Lie group sufficiently small. So for example, today we'll take it to be the trivial representation, and that's fine. And a complex number, which I'll call tau uv. There's an asterisk with this. Ask me later. There's believed to exist a corresponding n equals 2 supersymmetric QFT in 4 dimensions. That wasn't the place to put the n equals 2 supersymmetric 4D QFT. So I'll call it T of, depending on this data, so T of G, R, and tau UV. That's n equals 2 super Yang-Mills. Now in this theory, I told you that your space-time is supposed to depend on some data. So what's the data going to be in this case? So the space-time X, we sort of informally call the manifold that we put into the theory in the top dimension, we call it space-time, even though it's Euclidean signature. So all the dimensions are space. So the space-times that we're allowed to plug into this 4-dimensional theory, they're supposed to carry, so the big one, I guess we should put it first, a Riemannian metric. So this is not on its face a topological field theory. This is a physical field theory that depends on every detail of the Riemannian metric. A spin structure. And then something we don't always talk about is you can equip it with a connection for the group SU2 times U1. So this is what's called the global symmetry. So just about every n equals 2 theory that we usually talk about has this global symmetry group, sometimes called the R symmetry. In fact, maybe it's better to call it R symmetry instead of global symmetry. I'll call it R symmetry. And so when we formulate the theory on a spacetime, we're free to equip that spacetime with a connection for this SU2 cross U1. We usually take it to be trivial, and I'll take it to be trivial for a while.
When you say connection, you mean the traditional Lie algebra valued connection associated with the group?
Yeah, I mean, you pick a G bundle, pick an SU2 cross U1 bundle and a connection on that bundle.
Okay. All right.
Andy, if the U1 is anomalous, does it
that's
still
true.
make
Sometimes you don't
sense?
have the U1. Yeah, very good. Thank you. That's a good point. Let's forget the U1. I wasn't going to use it anyway. Thanks. Yeah, sometimes it doesn't have the U1 actually, but it almost always has the SU2. Yeah, great. Very good point. Great. Okay, so where does it come from? So how do you construct this theory? Well, this quantum field theory is the kind of field theory that you learn about like in your first quantum field theory course. So it's constructed by quantization of a classical field theory. I want to emphasize not every quantum field theory comes this way. And the ones we'll talk about later do not come this way. But these are kind of the simplest ones to think about at first. And they are the ones that are relevant for a lot of applications. So what does this concretely mean? It means that given X, we consider a field space, which is going to be some kind of space of functions on X. I'll say it more concretely in a second. But roughly speaking, you can think of it as some enormous space, because it's a space of like functions on this four-dimensional manifold. And an action, so a function which is called informally called the action, from this enormous field space to R. Let's say to C. So I don't know why I wrote R. And then we try to define so first of all, we would define the partition function zt of x, so which I wrote like this, as the integral over the field space. So we equip it with some carefully chosen measure, and then we integrate e to the minus the action, integrate over this enormous infinite dimensional space and get a number. And that number is supposed to be the invariant you assign to the four manifold. So some big integral. And then similarly, if we're given a local function O of x from F to C. So what do I mean by a local function? I mean, it involves evaluation of the field. So the fields are some kind of functions on X. And then you could consider, for example, if you had a field which was literally a function, you could imagine just evaluating that field at the point X. That would give you a function on the space of all fields, right? A function on the space of all functions that's the operation of evaluation at X. Or you could evaluate, say, the derivative at X. Or if you have a field that has multiple components, you could take various components of the field. So all of those are what I'm calling local functions. And given such a local function, we can also try to define so now I'll write zt of now the data of x with O of x inserted. This angle bracket E O of x is the integral over the field space where now I just integrate, instead of taking just the kind of overall partition function, I take a kind of expectation value of this function O of x, again, integrate over the whole field space. So that's again a number, at least formally, if all your integration works out. And similarly, you could try to define, if you have a bunch of these local functions, you could similarly try to define O1 of x1 up through O(n) of xn. Okay. So, okay, at least as a kind of formal exercise, I hope it's clear what kind of thing we're going to try to do, what kind of thing one tries to do. There are, apart from the sort of infinite dimensional nature of the story, there's two other little caveats that I feel like I should at least mention. So one is that in this particular field theory, I said that F is like the space of all fields. Calling it a space is maybe not the very best thing. So so you'll see when I tell you what the space of fields is, but just as an abstract statement, this F here is kind of most conveniently defined, most conveniently described, not just by giving a space in the ordinary sense. It's conveniently described by giving an overlarge collection of objects. And then a bunch of equivalences between them. Physicists would describe this by saying you have to mod out by the gauge group. But another way of saying it, which I think maybe is even slightly better, is to say that F is a groupoid rather than a set. Okay, fine. And then the second thing that hits you, when you really try to learn this. Sorry, what happened to my? Oh, it's the weirdest thing. I was scrolling my notes with a mouse. Now the mouse is gone. But how can the mouse be gone? Doesn't make sense.
This is telling me I might need to stick with external, by the way.
This is weird, right? Yeah, if you use Zernal PP, your mouse can disappear. Seems impossible. Okay, it's all right. I can solve this problem.
Is it worth just closing and restart? I don't want you to lose your notes though.
No, it's literally, I'm saying it's a physical problem. When I say my mouse is gone, what I mean is the actual physical object. Okay. Yeah, it seems impossible, right? Okay, anyway, so never mind. So the other caveat is that this space F is actually a superspace. So even if you forget this issue of it being a groupoid rather than a set, if you just think of the equivalence classes, then it's actually not a space in the ordinary sense. It's what people call a superspace. And so the function S from F to C, that has to be understood in the sense of supergeometry. After this lecture is over, if someone says they want it, I can like prepare some slightly more detailed account of this. But for now, I think it'll suffice to just say this. So in the case where the representation is trivial, which is the case we need for Donaldson theory, let me just say concretely now what this space of fields actually is. At least I'll tell you, I'm going to avoid this supergeometry by just telling you what the bosonic part of the space is. So the bosonic part of the set of objects of F what I'll call F bosonic. It's just the set of all tuples. So I'll write E, phi, and D, where so E is a principal G bundle over X with a connection nabla. So we're studying all bundles with connections over X. And in the simplest version, in ordinary Yang-Mills theory, that's all you would do. So the fields would just be principal G bundles with connection, nothing else. In this supersymmetric version of it, as it turns out, the G bundles automatically come with some additional stuff. Some of it is fermionic, and so I'm not describing it, but some of it is bosonic. And so in particular, what you automatically get is a section of the bundle. So here's our principal G bundle again. And now we take that principal G bundle, take the associated bundle associated with the adjoint representation of G. So I guess another way of writing this would be, maybe some people like this better, add E complexified. So locally, what that means is you just have a field which takes values in the complexified Lie algebra, but then it's twisted by this G bundle E. So those are the two things that are somehow important, but so I didn't want to tell you a lie. I have to also say that there's this object D, which plays a relatively trivial role. It's a section of, so it's also an adjoint valued thing. And if you want to learn about it, the buzzword for it is it's called an auxiliary field. Okay. Okay, so that's our set of objects that we're supposed to integrate over, except that we consider them up to equivalence. So the equivalences are just the kind of natural equivalences here. So if I have two G bundles with connection, I'll call them equivalent if I have a map from one to the other, a map of G bundles that preserves the connection and also preserves all the other fields. So, so the arrows in F are principal bundle maps from E to E prime. Maybe I'll call the map G, where G pullback of phi prime is phi, and G pullback of D is D, and G pullback of D prime. G pullback of nabla prime is nabla. I guess I could have written here D and D prime. I didn't have to put dots. Okay. So that's kind of the natural notion of equivalence here. And so we're integrating over all bundles with connection, but up to this equivalence. And then the action is, so S, so now the action is supposed to be a functional on the field space. So it's a function of E, phi, D, and the extra odd fields, which I haven't written. But let's, I tell you what, let's restrict to the bosonic part. So I set the fermionic fields to 0. So then I just have to literally write an action, which is a function of E, phi, and D. And what it is, up to factors of like 2 and pi and so on, which aren't super important, and I didn't try to work out. It's basically the norm of the curvature, the self-dual part of the curvature times tau, the anti-self-dual part of the curvature times tau bar, which has this kind of holomorphic nature somehow, plus the covariant gradient of phi, plus the bracket of phi and phi dagger, plus the norm of this D. I think that might be it if I only consider the bosons. So yeah, so as far as the bosons go, I think this is it. And So, okay. And okay, and the important thing from our point of view, or the first important thing, is that this action has a lot of symmetry. Okay, I see it's 4:02, so I'll stop maybe in 2 minutes. Is it okay?
Oh, yeah, and you could probably go for another 10 minutes because we started a little bit late with
Oh, that's true.
intake and
That's
things.
true.
Yeah,
That's
so-
true. Okay, great. So in particular, so what do I mean by saying that it has a lot of symmetry? Well, actually, from the way I wrote it, I guess you can see it's sort of manifestly, from the way I wrote it, at least the bosonic part, it's manifestly invariant under the isometries of X. Meaning that, right, the isometries of X, I mean, all the, I suppose all automorphisms of X actually act on this field space. So any map from X to itself would, by pullback, would give an action on this field space. But in particular, if your map happens to be an isometry, then it'll preserve all the structure that goes into the definition of this action, at least for the bosonic part. And I tell you, it's also true for the fermionic part, I guess, as long as this isometry lifts to a spin isometry, as long as it lifts to the spin structure. So what you can see easily is that this action is invariant under the isometries of X. So in particular, if X was just R4, let's think for a little while about kind of the simplest thing, which is the dynamics of the theory in R4. Then S is invariant under the spin isometries of R4. Yeah, so I'll write twiddle here to say I lift it to the spin group. So the spin isometries of R4, which I might write as, so it's the spin group, spin 4, but then extended by also the translations. So I'll write I spin, in the same way that people write ISO sometimes for the special orthogonal group plus translations. I'll write I spin for the spin group extended by translations. So that's the manifest symmetry, and that's a symmetry which you would have in any, in kind of the usual kind of four-dimensional field theory, would always have that kind of symmetry when formulated in R4. But here, this particular S is actually invariant under a bigger symmetry, is invariant not only under the under I spin R4, but it's invariant under a super extension of that. So it has more symmetry. So in fact, S is invariant under a super Lie algebra, what I'll call script A, n equals 2, d equals 4, extending the Lie algebra, so I spin 4. So that's what's called the n equals 2 supersymmetry algebra. Yeah, so let me write that algebra. So to write it, so I need a little bit of notation. So so the group spin 4, spin 4 is the same as SU2 cross SU2. That's the same Lie group. And so it has two inequivalent spin representations. For any spin group, you can talk about the spin representations. In this particular case, because the group is just SU2 cross SU2, the spin representations are something very concrete. Namely, it's just the two-dimensional representation of this SU2 or the two-dimensional representation of this SU2. So I'll call those representations S plus minus. So they're both complex and two-dimensional. Each one has an invariant skew pairing. So eta, say from S plus or minus times S plus or minus to C. And there's an intertwiner from S plus times S minus. S plus times S minus is isomorphic to the vector representation, the standard four-dimensional representation of SO4. So V is the vector representation of SO4. Well, it's a representation of spin 4 inherited from SO4. I'll write it like this, spin 4. So just using that kind of group theory stuff, we can write down this algebra. So to write it, because it contains I spin 4, it's a representation of I spin 4, and I'll write it, write what its content is as a representation of I spin 4. So here's what it is. So first of all, there's the I spin 4. There's an extra C2, which is central, and I'll talk about it in a second. So this is the even part. This is the even part. So it's a Lie superalgebra, so it has an even part and an odd part. The even part is basically just the original I spin 4. And then there's the odd part, which is kind of the interesting part. The odd part is 2 copies of the representation S plus and 2 copies of the representation S minus. So in other words, we add a bunch of new generators, which are parity odd. It's the super part of the Lie superalgebra. But as far as the rotational symmetries of space-time go, they transform as spinors. And by the way, this is the moment where you see the n. If you're wondering what n equals 2 supersymmetry means, 2 each of S plus and minus. That's related to the n equals 2. So if there's a similar thing you can do where you just take 1 copy of S plus and 1 copy of S minus. Then it would be n equals 1 supersymmetry. And I guess I'll just write the what the algebra actually is, and then I'll finish. We can pick up next time. So let me give the generators names. These generators I'll call Q1 and Q2, then Q bar 1 and Q bar 2. And then, so Q1 is supposed to be valued in S plus. So if I choose a basis for S plus, I'll have literally generators labeled by the basis elements. So let's write alpha for the basis element, in S plus. So alpha goes from 1 to 2. Since S plus is 2-dimensional, so I get 2 generators here. And correspondingly here, I'll have a basis for S minus. And so I'll have, so altogether here, I've got 8 generators, Q1 alpha, Q2 alpha, Q1 alpha dot, and Q2 alpha dot. So 8 odd generators. And then here, this extra C2 has generators that I call Z and Z bar. And these are going to be central. They commute with everybody. So I won't say anything more about their brackets. And then here, we have the rotation generators that I won't need a name for. But we also have the translation generators, and those I will need a name for. I'll call them P mu. So mu goes from 1 to 4. Literally just the translations in the 4 directions in R4. Okay, so now I can at least write for you the algebra. So the brackets of the odd generators are given by like this. The bracket of the Q's is the translation. The bracket of Q1 with Q1 gives a Q1 with Q bar 1, I should say, gives a translation. And likewise, Q2 with Q bar 2. And then the brackets of the Q's, that's actually the most important thing. This is the most important one here for our purpose. But the bracket of the Q's, of Q1 and Q2, will give, this epsilon is the Levi-Civita symbol. So it's non-zero only if I and J are both 1 and 2. And then we have this pairing eta alpha beta, and here appears the generator Z. So this central generator appears in the bracket of the Q's. The more important thing is that the bracket of a Q with a Q bar gives you a translation. Okay. So I think, so obviously we didn't get to the integrable system yet, but we'll get to the integrable system, I promise, by the end of tomorrow. So let me just summarize what we did so far. I told you a kind of story about Donaldson theory. I said that the Donaldson invariants turn out to be part of n equals 2 super Yang-Mills for the gauge group SU2. And I started telling you what n equals 2 super Yang-Mills is. And in particular, we wrote down this extended symmetry algebra, which this theory has, which will be the key to various things we do going on. Okay, I think I better stop, right?
Sure. Well, let's thank Andy for a terrific first lecture.
Sorry, I feel like I certainly meant to do more, but you know.
Oh, no, that's great. That's a good amount of material right there. Do we have any questions for Andy?
Could you explain again where the central part of the superalgebra came from?
Where it came from is an interesting question.
Like why it's there, I guess.
Yeah, why is it there? I think I better. I mean, you're right that actually when this superalgebra acts on the space of fields, that central generator is not going to act there. So in a sense, I don't need it at this moment, but I'm going to need it a little later when we write down the action on the Hilbert space. Yeah, and I guess then I should try to explain. But actually, I have to think a little to give a good explanation of why it appears in the Hilbert space and not in the space of fields. So in other words, I'm trying to put off your question by saying, well, this is for some future convenience. Yeah, which is okay. I think that's the best I can do right now. Anyway.
Okay.
Just looking at the chat here. A question just popped up from Sebastian. Sebastian, do you want to go ahead and ask?
Okay, sure. I was just curious about the auxiliary field. What does the C3 there mean?
The C3, okay, calling it C3 was kind of maybe too cheap. So it's really the so you remember that this whole theory has the SU2R symmetry acting on it. And that SU2R symmetry is almost invisible in what I wrote because I wrote only the fields in the theory without matter, with R equals trivial. And I only wrote the bosons. And in that situation, you almost don't see this R symmetry action at all. In other words, acts trivially on these fields, except actually for this auxiliary field D. And so this C3 is really the three-dimensional representation of that SU2 R symmetry. So that's where it would show up. I mean, concretely, if you wrote down like the superspace, description of this field, it would show up in kind of the high order part of the superfield. And so it's multiplied by a bunch of thetas. And so for that reason, it transforms under the SU2R symmetry.
So you take the adjoint representation tensored with itself?
No, this is, sorry, very important. This is a constant source of confusion in this business, is that there's the SU2, which is the SU2R symmetry, which I mentioned at the beginning. I said, any n equals 2 supersymmetric theory that we're going to consider always has this SU2R symmetry. And that's absolutely independent of which n equals 2 theory you consider. And in particular, that SU2 has nothing to do with the gauge group, which also happens to be SU2 in our basic example. So it's not here that we're tensoring the adjoint with itself. It's rather that we're tensoring the adjoint with another C3, which you might think of as the adjoint of the SU2R symmetry. Yeah.
Okay, cool. Thanks.
Wonderful. Are there other questions for Andy?
I guess I have another question.
Sure, go ahead, Elliot.
So when I have seen this stuff in the past, I've essentially just sort of disregarded the fermionic parts of the action as just like some, I don't know, some nonsense to worry about later. And it seems like you've done pretty much the same thing. So I guess I'm wondering, like can we safely just ignore those as like they provide symmetries, but they don't really have physical meaning, or like what's the deal with that?
I don't think it would be a good idea to think that they're somehow unphysical. I mean, they are absolutely an important part of this theory. It's just that there's this congenital laziness that physicists develop because it's kind of hard to remember exactly what you have to write. The notation is complicated, and it's somehow easier to remember the bosonic part. And for some purposes, it's true that the bosonic part is kind of the main part. So often, I mean, for example, here, when we do this localization, the localization is going to be on configurations where the fermions are, don't play a role. But it's funny to say, no, I don't think you should ignore the fermions, while simultaneously ignoring the fermions in my presentation of the action. But nevertheless, that's the position I take.
Okay.
That's an interesting question. Any others for Andy?
Have we seen at this point why our representation needs to be small enough?
No. I mean, in fact, I didn't. Here, I only wrote most of what I told you was in the case where the representation is trivial. But I'll tell you why the representation has to be small enough. It's because of it's nothing to do with the classical theory. When you write down the classical theory, you could pick any representation you want. But when you go to, then there's this important question of whether that classical theory can or cannot actually be promoted to like a full-fledged quantum field theory that exists in the continuum limit. And then there's a sort of crude first calculation you do, which is you calculate the so-called one loop running of the coupling. So you study roughly whether, if I study this field theory at different energy scales, whether the coupling will get stronger or weaker as I go to higher and higher energies. And what you want is that the coupling either stays the same or gets weaker as you go to higher energies. That would mean you have a chance of defining the theory at arbitrarily high energies, which is kind of the nicest situation to be in. It's what people call a ultraviolet complete field theory. So that one loop computation of the running, that turns out to depend on what representation you have. And roughly, if the representation is trivial or if the representation is sufficiently small, then the running goes in the direction you want, meaning that the coupling gets weaker at high energies. But if the representation is too large, for example, what too large would mean in this case of SU2 is more than 4 copies of the fundamental representation, for example. If it's too large, then the running goes the other way. And that doesn't mean that the theory is completely useless, but it does mean that its epistemic status is somehow a little worse. It's much less clear that the theory is really well defined.
Cool, thanks.
Great.
So if I could, I have a sort of just a broader question. So something you mentioned you were very careful about in the talk is when you said about the 4D theories, that there's no rigorous mathematical definition yet. And I'm curious, like, sort of what your take on this is. Like, are you saying that because you think that there will be one in the next 10 to 20 years? And like, what even would a rigorous mathematical definition look like for something like this?
Well, certainly I don't believe that these are like some eternally ineffable objects that will never be defined. So that's why I said yet, is I believe at some time they will be defined. Okay, now you're asking the harder question of 10 or 20 years. I think I'm not close enough to the people who are really working on this to really have a sense of that. I mean, I can say I feel optimistic, I feel like people have learned a lot, in the last few years. But, ultimately, at least, with the most naive way that I think about this stuff, I mean, there are some real analytic problems, and all the progress that's been made kind of in the topological world, it feels like it's pointing to like the shape of what the right definition could possibly be, but I don't see now that it leads to a new way of solving the kind of analytic problems. So yeah, I guess I don't want to say it'll be done in 10 years.
So like, would it look like, I don't know, defining some sort of virtual fundamental class on the space of fields, kind of like they do with, I guess, more topological theories, but it's infinite dimensional, or like, I don't know. I guess
mean,
like
you could separate,
how might it?
I think we should separate two things. I wasn't quite careful enough. I mean, there's one problem, which is just defining what you mean by a four-dimensional quantum field theory. And I think even that hasn't been done. And then there's the problem of constructing an example of a four-dimensional quantum field theory. And I guess it could be that you could do one without the other. In other words, it could be that you could find the correct definition in this sort of fully extended kind of functorial QFT way. But that, like I said, I think, again, I'm not like the world's expert or even close, but I feel that a lot of progress has been made in that direction in the topological field theory world. I don't think that it's been done yet in the Riemannian field theory world. So you can imagine that will be done. It's easy to speculate. Yeah, okay, I would be hopeful that that'll be done. I think it hasn't been done yet. But then the problem of analysis, the problem of showing that Yang-Mills theory actually gives you a theory, that still seems hard. But again, I'm not the guy who's really most equipped.
Yeah, thank you. That was interesting to hear.
Sorry.
So if I can add a quick thing to that question. So perturbatively, there has been a great deal of progress. And I guess I'm thinking particularly about sort of BV and factorization algebra approaches most recently. And the issues that arise mathematically are sort of the ones that you would expect to arise physically. They're issues of regularization as like operators get close to each other. What do you even mean by a local operator at a point? So some of these questions have been answered to the extent that one can compute like the running of the gauge coupling with scale. Which has to be there for any sort of mathematically reasonable treatment. But then non-perturbative issues and like things like accounting for instantons or the low energy behavior of QCD, where couplings get very strong, has not been dealt with. I think those are the really hard problems. That's the $1 million millennium problem. Asymptotic freedom in QCD.
Yeah, and you know more about this than me. I mean, do you have the impression that, so it's clear, and I should have said this, you're right. I mean, in perturbation theory, we're much better off than we were. But does any of that stuff help you at all with like the non-perturbative stuff?
Not that I can tell. I haven't seen any claims to that it does yet. Like it was like hard enough and impressive enough to even get like the perturbative sector.
Oh yeah. None of this is to take
Yeah.
away from what's been achieved, which is indeed quite spectacular.
Interesting. Since you'll be talking about integrable systems, just out of curiosity, as a preview of forthcoming attractions, is this point of view of finding a connection to integrable systems possibly opening up some new ways of looking at the original theory?
Yes. You mean like to what extent does knowing about this integrable system help you to understand the four-dimensional Yang-Mills?
Correct.
But you're asking how much does it help you to understand the non-abelian theory kind of intrinsically?
Right.
Yeah, that's an interesting question. Right, this integrable system, how much is it about the effective theory and how much is it about actually secretly about the non-abelian theory? There's a little bit you can say about the non-abelian theory that okay, maybe ask me again after I've tried to say what I think is.
I promise I will. So I've been
Very good.
always thinking in some sense about the integrable systems as something that is very important when you are close to equilibrium. So in some sense, when you are close to a stable equilibrium, essentially any system is an integrable system, is a bunch of harmonic oscillators or some version of that. So integrable systems play an important role for certain specific configurations. But the question is, how much do they capture information about the whole theory, not some region of theory?
Right. Yeah, this is a reasonable question. I think you can at least say what the integrable system is in a language that doesn't involve the infrared. But I
will ask you the same question, I promise.
Okay. Who am I talking to, by the way? I can't see.
This is Jacek.
Hi.
I'm Steven's colleague.
Yes. Hi. Yeah. Since you said the word new, I should say that this integrable system is not something super new. It's it's the thing that Seiberg and Witten and people shortly after Seiberg and Witten discovered.
But
recently,
this sort of idea of somehow integrable systems popping up in quantum field theory is continuing. It's not a. I mean, I actually like integrable systems, so I hope that this connection is not dead.
No, definitely, it's a very active. People are doing new things with it, but I'm just saying the original idea is.
Oh, beautiful. Do we have any further questions? It's sort of time to transition, I would say, to the next talk. So if there are no burning questions, we have lots of time over the week to discuss as well. So maybe we'll just thank Andy again. Fabulous talk and a really, really lively question period.
Thank you.
So thanks not only to Andy, but to all of you, asking great questions. That's what this summer school is all about. And maybe we'll take, 2-3 minute break so we can transition.